Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Roxana Lupu, who's come across to us from NASA Ames. She's a principal investigator at the Bay Area Environmental Institute, Research Institute, and she did a BS in physics at the Alexander Ioan Cuza University at Iași in Romania, and then came across to the United States to do a PhD in astronomy at Johns Hopkins. Her topic was molecular fluorescence in diverse astrophysical environments. And then she did a postdoc at University of Pennsylvania, and then did a postdoc with SETI and over at NASA Ames. Her research has revolved around molecular spectroscopy, including detections of formaldehyde and carbon monoxide in comets, in the ISM, the interstellar medium, and in Jupiter. She's also looked at high redshift detections of molecules and using spectroscopy. And now she's, as we're going to hear about today, interested in atmospheres of hot and rocky planets. In the past, in the future, and far and beyond. So she's going to talk to us today about terrestrial planets after giant impacts. So please join me in welcoming Roxana.
Thank you for a very nice introduction. I'm glad to be here and present you the work I've been doing at Ames. With my collaborators, Mark Marley, Kevin Zalny, and Richard Friedman. Kerry Cahoy started this project also at Ames, and then she moved to MIT. We have collaborators at UC Santa Cruz, Caroline Morley and Jonathan Forney, and the chemistry grids that I'll be showing have been produced by Bruce Fegley, Catherine Rothers, and Laura Schaefer. So planets after giant impacts, what is the big picture that we are going to look at? So current planet formation models state that the giant impact era occurred at the end of terrestrial planet formation, and it took about 40 to 100 million years, during which to form a planet like Earth, planets have undergone of order of 10 impacts. After each one of these impacts, the planets are left hot for a long period of time. So we might have a chance of detecting some of these with the new upcoming instruments, such as the coronagraphs on 30-meter class telescopes. The classic example of a giant impact is the moon-forming impact in our own solar system. So I have a little movie showing kind of what is our picture of what a giant impact would look like. Basically, we have two young planets of roughly the size of Venus or Mars, and they collide, and in the aftermath we have some debris produced, and also the planet formed is left hot, covered by a magma ocean. The debris might or may not form a moon. So why are we interested in this? As I mentioned, future instruments might be able to detect some of these planets. And preliminary calculation show that for every 10 to 50 stars, we might find one planet that is in this post-giant impact stage. And this depends on our knowledge of how many terrestrial planets we can find per star and how many impacts happen during this 40 to 100 million years time period. So there are a lot of assumptions, but we hope that the contrast between such a planet and the host star might be somewhere in the 10 to the minus 7 and 10 to the minus 5 range, such that some of them would be observable with the current Gemini planet imager, which has just come online, and many more of them might be accessible with a 30-meter telescope. This slide shows a prediction based on the model for the Earth in the aftermath of the moon-forming impact, showing that we expect that after roughly 10 to the 4 years after the impact, the surface temperature reaches 20,000 plus Kelvin, and then it slowly cools, while the radiating temperature of the planet, due to the opacity of the gases in the atmosphere, is only between roughly 600 and 250 Kelvin, and therefore it slows down the cooling of the planet's surface. So by improving these models, we will be able to establish a better relationship between the surface temperature of the post-giant impact planets and the observable radiating temperature. So there are only a couple of models that have addressed this in the past, namely the Alan Stern in '94 and Eliza Miller-Rich in '09. But we're going to vastly improve on these models, particularly because we take into account very self-consistent equilibrium chemistry of the gases in equilibrium with the hot rocks and magma ocean, while these other models just assume a water and CO2 atmosphere, and often they just include a gray opacity, while we include all the opacity available for the gases in equilibrium with the magma ocean. Our model is a simple one-dimensional radiative convective equilibrium model, and it uses the correlated K coefficients method for the radiative transfer to save time. Let's start with the chemistry that we're using in our models. So basically, we are looking at two possible compositions of the magma ocean. One is comes from melting the continental crust, and the other comes from melting the bulk silicate earth, which is basically the crust plus the mantle plus the ocean and the atmosphere. So the basic difference between these two compositions is that the continental crust is more oxidized, and also there are differences in the iron, aluminum, silicon, and carbon abundances between the two models. So basically, assuming this rock composition, we can break down into an elemental composition and then compute the equilibrium chemistry for these elements as a function of pressure and temperature. And this is the model presented in this paper by our collaborators. And they explored the regime between 300 and 400 Kelvin up to a pressure of 100 bars. In these models, 110 species are considered. But here is an example of the equilibrium composition that we have, for example, for the continental crust chemistry at a pressure at 1 bar as a function of temperature, you see that the main components are water and CO2, and then nitrogen, and after that SO2 and alkali and hydrogen halides. For the bulk silicate earth as, at the same pressure as a function of temperature, we still have a composition dominated by water, but at the lowest temperature we have a big contribution from methane and ammonia, while other molecules that we've seen in the other case are also important, such as SO2, HCl, HF, and sodium chloride, and so on. Of course, we don't have opacities for all possible 800 molecules in these models, but we have the opacities for most important of them. And this is what we include in total at 33 molecular opacity sources. And of course, you see here the methane, the water, CO2, ammonia, SO2. We also have opacities for the alkali metals, and we include the collision-induced absorption as available from the high-train database. This basically includes collision between the CO2 molecules, the oxygen, nitrogen, and methane molecules. The model also includes Rayleigh scattering, but at this stage we don't include clouds. So the parameter space that we explore has a range of surface temperatures for the hot post-giant impact planet between 1000 and 2000 Kelvin, with two possible surface pressure, 10 and 100 bars, for the two compositions that I've mentioned, and two possible surface gravities. And in all these models, we just assume that the planet is illuminated by a sun-like star at a distance of 1 AU. So these are the results from the 1D model, basically giving us the temperature pressure profiles. You can see as a function of surface temperature on the bottom, from the hottest to the coldest model. For the two surface pressures, this you can see extend to higher surface pressures. The profiles for the two surface gravities are very similar. Essentially, these models show that the atmosphere has an isothermal part at the top, and then a radiative convective region at the bottom. And we determine the size of the convective region in here by adjusting the size until the lapse rate is smaller than the dry adiabat. The only species that condenses in this model is sodium chloride, so it doesn't affect the energy budget much here. So the dry adiabat is a good approximation. Another thing that you see here is that for the bulk silicate earth composition with a high surface pressure, the pressure temperature profiles pile up at the lowest surface temperatures, and we developed a small constant temperature zone here at the bottom, because the composition does not allow the adiabat to become steeper. As you saw, the top of the atmosphere and all these models tended to the same temperature here, but this is just due to the sun being fixed at 1 AU. If I vary the distance of the planet from the sun, for example, 0.3, from 0.3 to 3.3 AU, you can see that the temperature at the surface of the atmosphere changes. The closer it is to the sun, the warmer the top of the atmosphere will be. However, this does not affect much the radiation from the planet, because most of the radiation will come from here. So you see most of the spectrum is the same, especially, except for the Rayleigh scattering part. So this is proportional to the amount of solar radiation that the planet is receiving. As I said in the beginning, these models allow us to derive the relationship between the effective temperature and the surface temperature for these post-giant impact planets. And you can see that these relationships have different slopes based on the composition of the atmospheres, and also that the models with higher surface pressure have smaller effective temperatures. Also, for the bulk silicate Earth case, as the planet cools down, we form more opacity sources in the atmosphere, and we reach a regime, namely the runaway greenhouse, where the planet is unable to emit more than 265 Kelvin, and basically the effective temperature that we see is decoupled from the surface temperature. It's a degenerate solution in the sense that as we measure an effective temperature for the planet, we have no information of the surface temperature from that. This is how the spectra look like from the atmosphere structure code. This is a relatively low resolution spectrum, but you can still see the main properties. You can see the brightness decreasing as a function of surface temperature, but also note that even if these graphs are in surface, in brightness temperature units, which basically is the equivalent temperature of a black body emitting the same amount of radiation at a specified wavelength. So you can see that even though, for example, this model has a surface temperature of over 2000 Kelvin, at a few microns it only emits as a black body of 1000 Kelvin, and so on. So only in the visible, the brightness temperature of this planets approaches the surface temperature. And these units are nice because they basically tell you from how deep in the atmosphere the radiation is coming from. So basically only the visible wavelengths have any information or are close to the information about the surface temperature. Going back to the chemistry, based on the pressure temperature profile, we can compute the abundances of the components at every place in the atmosphere, assuming chemical equilibrium. So you see as I showed in the previous slide just from the chemistry grid, that the continental crust case is dominated by water and CO2, and then at the bottom of the atmosphere we have, at the highest temperatures, we have HCl and SO2, and well, I guess I didn't put HF in here. For the bulk silicate Earth case, because of the changing chemistry as the lowest temperatures, the top of the atmosphere will be dominated by CH4 and ammonia, the water abundance drops, and also the CO2, because most of the carbon now is in CH4. This is probably not surprising because the same composition corresponds to the volcanic gases that we can measure on Earth. This is, for example, a measurement of the SO2 cloud from the Etna volcano in Sicily. And this, of course, all these gases are very dangerous for life. And there have been some theories that they might have caused mass extinction just from the long erupting million years long eras. So if I get back here a little bit, you can see that even if the measured temperatures of these planets can be around 300 Kelvin and the composition is water dominated, the surface can be very hot and also the composition is not very favorable to life. So basically a planet that otherwise would be in the so-called habitable zone and have other measurements pointing at the presence of life might in fact not be habitable because it might be one of these post-giant impact planets. The composition is also similar to what we see in Venus. Venus is the hot rocky planet in our solar system, the sister of our own Earth, and I'm sorry I couldn't find a better spectrum. I would like to have one, but basically from the models and eliminating all other spectral signature, people have inferred the presence of HCl in the atmosphere of Venus. Also, the spectral retrieval from Venus Express have produced vertical profiles of some of the important molecules, and you can recognize here SO2, HCl, HF as in our models. However, our opacity database is very high resolution, so we can produce high resolution spectra for all these planets and identify all the features that we can see in their spectra. So you see all the water features, mostly at shorter wavelengths, CO2 and some CH4 is identified here. The short wavelengths for low surface pressures, we have the signature of sodium. So for the continental crust, mostly the water and CO2 are dominating. Now let's compare it to the bulk silicate Earth case. In the bulk silicate Earth case, we have the additional contribution of CH4 and ammonia, and notably the the bands of CO2 and water do overlap at some level, but the CH4 brings a lot of opacity in the water windows. So you can see how the emission drops significantly in these water windows as we add CH4. So that's basically why we reach the runaway greenhouse limit in the BAC case and not in the continental crust case. Now, if we zoom in and look for smaller contributions to the spectra, I did this exercise while I subtracted an opacity source and to see if it has any effect on the output spectrum. So when you look like at a spectrum that where the HF was removed, the one in red, relative to the full spectrum, you can clearly see that this series of lines are due to HF and so on. So here the green is the spectrum with the HCl removed, and the blue is the spectrum with SO2 removed. So clearly these features come from HCl here and SO2 here. And SO2 might be one of the best molecules to look for in order to differentiate between a regular water planet and a post-giant impact Earth. Let's look how our models compare to the previous ones. This is in black is a model from Eliza Miller-Ritchie, which just considers water and CO2 in the atmosphere. And you can see that even for the continental crust case, where we don't have that much CH4 and ammonia, the brightness temperature at the peaks is already a factor of 2 lower than in the previous models, and that's just due to the new opacity sources. So basically that means that these planets are going to be more challenging to observe than previously thought. So what can we say about their detectability? We can compute the colors and the magnitudes for these planets and see how they compare with previously measured directly imaged planets right here, and these are brown dwarfs. These lines show correspond to the 10 to the minus 8 contrast for a 10-meter telescope around an M1 star and around a G2 star. So around a colder star, we can start to see more of this kind of planets, but we still need a 30-meter telescope, and we have to could go down to a 10 to the minus 8 contrast. Another complication in detecting these planets is the possibility of having a debris disk. And this is not the debris disk that formed the moon, because that dissipates on a time scale of around 1,000 years, but the debris that are going to trail the planet and basically orbit around the star. At a distance of 1 AU, this debris disk will have a temperature of about 278 Kelvin, and these are the black body curves for this temperature. However, so you can see that with this temperature, it wouldn't be hard to distinguish the spectral features from the planet. However, the disk will also scatter the light in the visible, but we don't know much of the scattering properties of this debris disk in the visible. And this is basically because measurements of debris disks look kind of like this, where this is the star and this is the debris disk, and you can see the different temperatures of the two black body curves. So the optical part of the spectrum is dominated by the star. So we can't, in low resolution observation, we can't distinguish the two spectra from each other. So basically, having a debris disk with strong visible scattering will add noise to our observation, so we'll have to go much deeper, or again have a bigger telescope so we can spread out the light from the disk over more pixels and get a better contrast to the planet. What does our curves of the effective temperature versus surface temperature tell us about the thermal evolution of the planet. These curves are similar to the ones I showed in the third slide. So we compute the energy balance between the incoming solar radiation, the heat flux from the interior of the planet, and the blanketing effect of the atmosphere. So the heat flow from the interior is basically determined by the convective motion, and at a temperature of about 1560 Kelvin, the mantle starts to congeal, which means that there is a phase transition in which the viscosity suddenly becomes a lot larger. So from behaving like a liquid, the magma starts behaving more like a solid, and this is the phase transition you see here. So that basically stops the heat flow from the interior to the surface, and the surface temperature will become decoupled from the interior temperature and just cools through the atmosphere. So that's what you see here. And the time that the planet will stay hot will be determined by when this transition occurs. And in the BAC case, this time is much longer because it enters that runaway greenhouse where the planet cannot radiate much. In the continental crust case, it's much shorter, of a few times 10 to the 5 years. But even though the planet in the BAC case stays hot for longer, it will still be more difficult to observe because its brightness temperature will be lower. We can apply this method to look at the evolution of the Earth's moon. And this is the canonical picture we have about the moon formation after the giant impact. We have a debris disk, and in a time frame of about 10 to the about 1,000 years, the material accretes to form a moon. But what happens afterwards is that the Earth and the moon are tidally coupled. So in addition to what I showed in the previous slide, we have a tidal energy term in the equation. And the energy is dissipated by tidal friction, but only at a rate that is determined by how fast the energy can radiate through the atmosphere. Also, by tidal coupling, the spin of the Earth goes down, but by conservation of angular momentum, the moon recedes from the Earth. So this is basically the picture, and these are just some preliminary calculations of the size of the semi-major axis of the moon and the recession rate of the moon based on these atmospheric models. And we find that if we take into account the atmosphere, and with such a big greenhouse effect, the moon recedes between 100 and 1,000 times slower than was thought based on previous models. So what conclusions we have so far is that these post-giant impact planets might still be good candidates for direct imaging, but we are going to need 30-meter class telescopes to observe them, because including all opacity sources shows that they will be less favorable to observe than thought based on previous models. And we have identified the markers of such post-giant impact planets, namely HF, HCl, and SO2. However, there's a problem. The problem is that what we considered so far was just equilibrium chemistry. But there are these equilibrium processes taking place in these atmospheres. One of them is vertical mixing and the other is photochemistry. Vertical mixing is basically due to the convective heat flow in the atmosphere, and is parameterized by this Eddy diffusion coefficient called KZZ, which depend on the scale height, the convective heat flow, the mean molecular mass, heat capacity, and density. And I put an index Z here to show that these quantities varies with height in the atmosphere. So we can estimate the magnitude of this Eddy diffusion coefficients. First of all, the scale height of these atmospheres is between 30 to 40 or 40 to 60 kilometers based on what composition you assume. So that gives us a KZZ of about 10 to the 8 centimeters squared per second, which is comparable to what we see for the atmospheres of Jupiter and Saturn in our solar system. KZZ in turn can be converted into a dynamical time scale, basically by looking at the scale height and see how fast the material can turn over in one scale height. And it turns out that this dynamical time scale is somewhere between 1 and 20 hours, depending on what composition you assume. So that's pretty fast, and that's both good and bad. It's good because it tells us that the atmosphere does see the surface very often. So the composition would, the assumption of the equilibrium with the magma ocean is a good assumption. But at the same time, it's so fast that some of the equilibrium reactions that we assumed will be much slower. So those, the formation of some molecules will be quenched. So the victims of this vertical mixing are CH4 and ammonia. So that disturbs the entire composition of our bulk silicate Earth case. The chemical timescale for these reactions equals the dynamical timescales when the temperature reaches somewhere between 900 and 1000 Kelvin. So looking at our pressure temperature profiles, this happens at a very low atmosphere, very low in the atmosphere for this cold models, and somewhat higher in the hot models. So starting at this level, the composition, these reactions are quenched. So the relative abundance of CH4 and ammonia will stay fixed at whatever the equilibrium chemistry says it is at this temperature and pressure for this model, and at this temperature and pressure for this model. We also have photochemistry that changes the chemistry of the top of the atmosphere. And we use a code that contains both the photochemical reactions and the vertical mixing to determine the new composition that accounts for this equilibrium. This kinetics code contains 1100 reactions, but of the most important species, but still it's missing fluorine and potassium because it wasn't built specifically for this post-giant impact Earths. It also accounts for the formation of aerosols, but not for grain chemistry or dissolving HCl and sodium chloride in water clouds. So this is how the composition of the atmosphere changes when we apply this disequilibrium model. But you have to be careful here, because the disequilibrium chemistry model is not self-consistent with the pressure temperature profile, in the sense that the changes in the relative abundances will change the opacity of the atmosphere. That is not taken into account deriving the pressure temperature profile. So this is assumed constant in passing from here to here. And this is something that we will have to address in the future. So as we saw from the chemical and dynamical timescales, corresponding to a temperature of about 1000 Kelvin, we have this pressure. So above this pressure, we should expect that the reactions get quenched. So indeed, you can see the profiles of the relative abundances go straight, which means that we'll have less CO2 that doesn't get to dominate in the upper atmosphere, and less N2 that again doesn't change vertically. But because the specific constituents like HCl and SO2 are very abundant at high temperature, and the mixing helps them reach the surface of the atmosphere, then we get an overall a bigger column of HCl and SO2. And it's not shown here, but the same happens for HF as well. Here I also plotted the abundance profile for the sodium chloride going from gas phase into solid phase. So we'll have sodium chloride condensing, so we might have salt clouds, but or salt dissolving in water clouds. For the BAC composition, again, you see here the line corresponding to the level where the quenching occurs, and so the compositions, the relative abundances are frozen in at this level. So you can see the abundance profiles going up straight, but that means that we reduce significantly the amount of ammonia, and the CH4 is not even in the graph anymore. Also, CO2 and water increase, which make the BAC models more similar to the continental crust ones. Again, SO2, HCl, and HF are mixed throughout the atmosphere. So what changes does that produce to the spectrum that we expect to see? Here is the BAC case and the continental crust case. So in black is the original one, and in pink the model after changing the abundances. But again, I haven't changed the pressure temperature profile. So you can see more emission in the water windows. And for comparison, I put in gray the continental crust case. So they start to look more similar. The effective temperature of the new models is also about 50 Kelvin higher than in the original. And that's because of the removal of CH4 and ammonia. We can see that the SO2 and the CO features increase, and this change is even more obvious in the continental crust case, where basically the water and CO2 features remain very similar, but increasing so much the abundance of SO2 leads to this spectral signatures being even more prominent than before. And again, you can see the similarity between the continental crust composition and the BSE in the blue and the light gray. In this case, the effective temperature actually drops because we have more opacity due to SO2. So the next step will be to make everything consistent. The pressure temperature profile and the compositions taking into account the disequilibrium chemistry. But the original models are valuable in the sense that they brought to our attention how important the disequilibrium chemistry is. So the conclusions, the first set of conclusions stay the same, but now we know that the BSE case might be in fact more favorable to being observed, more similar to the continental crust case. The HF, HCl, and SO2, we verified that in both equilibrium and disequilibrium chemistry, they are important markers, and SO2 is an important opacity source. But we quench CH4 and ammonia formation, and therefore we don't expect to observe them. And we still need to add some opacity sources such as clouds into these models. So I want to leave you with the big picture where this work can be applied, namely, and some of the future directions to explore, namely the terrestrial planet assembly, the hot rocky worlds which form a big chunk of the planets, transiting planets being observed. Models for Venus-like planets, the origin of the moon, even habitability in the sense that I explained above that the planet being the habitable zone and having a cool effective temperature does not necessarily mean that it hosts life. And then these models pointed out the importance of the disequilibrium structure, the fact that we need to address the outgassing of the magma ocean and the escape of the atmosphere, and also look at more possible compositions. Thank you.
If you have a question for Roxana, put up your hand and I'll get around to you. I'll ask the first question. Roxana, going right back, I guess, to the start of your talk, the time that we're looking at is post-core formation of the planet. So
yes, it's the final stage of the terrestrial planet assembly. Right. So they accreted most of the material in their accretion zone, and then we have left this Mars-sized planets, right, that
and the magma
collide
ocean,
with each other. I'm sorry?
And the magma ocean that was originally on the planet has solidified, so it's post-magma ocean solidification.
Yes.
And then you're turning it into a magma ocean with the impact.
Yes. Yes, we don't really look at how the energy or how much energy was deposited. We just start from the magma ocean being there. But it's true that these models can be applied to other situations where the young planet hasn't lost its accretion energy, and the surface is still hot with the accretion energy. But we have to think whether the composition is would be the same, or we need to adjust the composition based on the material being accreted.
Right.
So because that would give us the composition of the magma ocean and the gases that would be in equilibrium with that.
Okay. And the continental crust, you're talking about modern continental crust.
Yes, yes.
Have you has anyone looking at Archean crust?
Not that I know
okay.
of.
Right.
Yeah.
Okay. Next question.
Roughly speaking, how much of the heat that's still in the Earth's mantle today is left over from these impacts that form the Earth, and how much of it is from the decay of radioactive elements?
I think the energy from the decay of radioactive elements is, at present day, it's really small.
Other questions?
Would you care to speculate on how this theory might give you some ideas about why Earth and Venus turned out to be so different?
These models in particular don't tell us about that. I don't think there is any model in which Venus has suffered a giant impact, but maybe a non-moon forming impact would have been plausible. But I think an essential aspect of why the Earth and Venus are different is the different distance from the Sun. In all my models, I put the planet at 1 AU. Now, one of my future projects is to look at hot rocky planets that are very close to their star, and maybe look at other situations in between. So that's, yeah.
Hi. How would the, if you'll pardon the pun, late heavy bombardment impact this model? And would any of the remains of the protoplanetary disk of our solar system have had any effect on this collision of the Earth, one that formed the moon?
I think that currently the models don't predict any significant amount of material being accreted after the moon forming impact. So both the Earth and its impactor have accreted their materials before the impact. These models have no memory of how that material was accreted or what it was.
Okay, I've read on the internet that the theory is the theory that Mercury, which is mostly a dense iron core, high density, and has lost its mantle, had its mantle stripped away by an Earth-size impactor. Does that make any sense in this model? And what could have happened to that Earth-size impactor, or could it have even have been Venus?
I haven't read that theory.
Okay.
I'm sorry.
All right, any more questions? No?
County, but I was going to ask, it said, I read that back in the day that the solar system showered the Earth with platinum meteorites and gold, but I strongly believe it was platinum and meteorites and gold comes from the Earth. Do you believe that?
I know that there are lots of iron meteorites. I don't know about gold meteorites.
I don't believe that.
There's got to be some. You just got to get a concentration mechanism.
Yeah.
Yeah. Okay.
Yes. Is there a description of this model on the internet or something?
There's a paper. I wrote a paper, so it's been published in UpJ You can find it on AstroPH archive.
You mentioned in your presentation that the debris might or might not form a moon. Is there anything in your model that you change and definitely creates a moon or doesn't create a moon?
No, the models just look at the planet in the aftermath of the impact. They don't look at the debris at all. The results I mentioned come from other simulations that actually simulate the impact and the accretion after the impact, and there are a lot of initial conditions that go in there, like the relative distances, the spin, angular momenta, and basically I think a moon only forms in about 8% of the cases.
Okay. Roxana, we have a special SETI Talks mug here for you, especially to fill with your favorite, hopefully not just atmosphere, but put a little liquid in there as well. That should work great.
Yeah.
Please join me in thanking Roxana for a great talk.